So we welcome now Maria from Graz University. She will talk about challenges in tool-based cryptanalysis. Thank you.
Thanks a lot for the introduction. So I gave a relatively vague title to my talk, and I will also try to keep the statements I'm making a bit more vague than some of the previous talks. So the main thing I set out to do is I noticed that while working with different tools, including some of the ones we've already heard about today, such as SAT solvers, SMT solvers, or also dedicated implementations, I've often repeatedly run into the same type of issues that occur in different areas of cryptanalysis, but that seem to have something in common. And I tried to pick out a few of those, and I want to give a bit of an overview. I will sometimes include some small cryptographic or cryptanalytic examples of where this shows up, but without going into too much detail. And overall, one of the main goals is that in the end, I'd like to, at some point in the future, see some kind of ideal cryptanalysis framework or an ideal collection of tools where ideally we can implement all kinds of ciphers that we care about. We can implement general descriptions of all types of attacks that we care about. And for each such combination, ideally, we find optimal attacks with all the known techniques that we have at the moment. And of course, we would like this to be extensible. So whenever we add a new cipher description, ideally, this works perfectly with all of the known attack techniques and vice versa. If we add an attack description, ideally, it works perfectly with all of the currently implemented ciphers. So what challenges do we have on the way there? So I've tried to separate these challenges into a few different categories or layers of the modeling and solving process. And the first of these layers is how we actually represent our ciphers. Now, there are a few relatively straightforward answers to this. We've already heard a bit about modeling, but I do think that there are a few ways we can improve this still, or a few challenges with the current models that we are choosing. And one of the core questions in this context is, what is the right abstraction layer on which we should model our scheme? I'll get a bit more concrete on this in a moment. And unfortunately, in several of the challenges that I'm listing, it's a sort of a trade-off question. So we've already heard the claim of Hossein's mom earlier today, that if you get one thing, you need to lose another thing. And this is essentially what the trade-offs are about. So in case of cipher representation, the trade-off is very often between simplicity and versatility to support, for example, different kinds of ad hoc techniques or things like that. Okay, but of course, we don't only want to describe the ciphers, we want to find something. And when we search for things, one of the main areas where we can often still optimize or improve our results is in terms of precision. Now, precision means, among other things, what kind of assumptions we are making when we are modeling, for example, the cost of our attack. And also to what degree of detail we want to analyze things. It's again a trade-off, and usually the trade-off has been between efficiency of the solving approach or of the size of the modeling description on the one hand, and the quality in some sense on the other hand, or the precision of our results. And very often, of course, efficiency is more important than the detailed quality because, for example, we only want to get some rough bounds or an intuition about how much we can expect for a particular cipher. And finally, there's another question, and that is the scope of the results we're looking for. So by scope, I mean, what is the answer actually that we're getting out of the tool? Currently, the answer is very often that what we get out of the tool is the description of a distinguisher. Like, for example, we get one differential characteristic, which allows us to set up a differential distinguisher. But we can try to get a bit more. So we've already heard today quite a few talks which try to include the key recovery part into the whole model. So this is one direction in which we can increase our scope. We can also increase our scope in terms of techniques. Now, this is particularly relevant on the key recovery or full attack side, because there are so many different ad hoc techniques that people have come up with. And Maria talked a bit about this in her talk. So defining the scope also defines, for example, in what sense the results we are finding are optimal, because they're always only optimal with respect to what we have modeled. And so if we extend the scope, we get more relevant notions of optimality. But of course, we can't put everything into one model, so it's a question of feasibility, how far we can get. All right, so I'll go through these one by one and give like one or two examples for each of these categories. So let's first look at the cipher representation level on this simplicity versus versatility trade-off. Now, of course, we have quite a good idea of what our ciphers generally look like. We reasonably agree on that. We have a few general construction paradigms like, well, very often we're just looking at key alternating SPNs, which might be on the strongly aligned side like AES, or slightly weaker aligned like present, or they might be examples of LS designs like ASCON, for example, with very weak alignment. Sometimes we have feistels, and feistels, interestingly, do often have quite different properties when we model them in tools. And we have some other considerations that can make modeling a bit of a pain, like, for example, if we implement reflection ciphers. At least on the practical side, when you actually try to write the models and try to write them as generally as possible, then reflection ciphers show you that you do need to make a few choices when you actually write down your cipher. So this is the high-level construction, and then we usually have some operations. And I would say this is typically the level of detail in which we describe our ciphers for a tool. So we say things like, here's an S-box layer with a few S-boxes, or here's a linear layer, and maybe we know some things about the linear layer. So we know not only its definitions, but some of its properties, like an MDS property, for example. Or in the ARX world, we have some different operations. Usually this last one doesn't really enter the picture, but Leo talked about it a bit earlier today, namely that some types of cipher designs are currently not represented in our tools at all. And this is mostly the case for designs that work in larger fields and that often come with their own construction paradigms, which are a bit different from what we see in the more mainstream designs, let's say. And finally, of course, inside our tool, what we often do is we specify a cipher on this layer here, but we let the tool translate it to this layer here. So we decompose it into smaller functions that we can model more easily. But this sometimes comes with a few problems, and we've actually seen examples of this today already. So we often need to decompose to get small building blocks that we can model in a locally perfect way, but this locally perfect way isn't necessarily globally perfect. So one example of this where there's a certain loss of information was, for example, in Patrick's talk when he described how these indirect contradictions work. And effectively, part of the information that we had was a bit lost in this model. For example, the fact that this AS operation in the middle, this mixed columns matrix, is an MDS matrix and thus has some properties. Another case where we have this loss of information due to the modeling layer we are choosing is in the context of the division property, for example, where we often have the challenge that modeling the linear layer is difficult. And if we decompose it into branches and XORs, the result is not necessarily optimal or as accurate as we would like. So what would sometimes help in a tool is if we could not just write down one type of specification, but if we could add additional knowledge about the design. So knowledge such as, for example, we not only have these individual bijective operations, but there are larger sections of the state which are a bijection from one to the other. This is sometimes we can sometimes exploit in attacks, particularly in, for example, impossible differential attacks, where we know that not only a particular cell, for example, must be non-zero, but for example, one column must be non-zero or something like that. These are properties which can easily get lost. And if we also sometimes care about different representations. So for example, of an S-box, sometimes we are happy with modeling the whole S-box based on its DDT. Sometimes it's more efficient to model it on a gate level. In some specific cases, which in cryptanalysis we maybe don't care about that much, we want to have a specific representation. For example, we want to represent the S-box as a composition of smaller bijective functions. For example, in a masking context, this is relevant. So being able to overlay different representation levels of a cipher for a tool, I think could be generally helpful if we want to then be able to combine this description with many different cryptanalysis properties. A related topic is not on the level of granularity, but on the flexibility of the presentation. Because one thing that we like to do a lot when we do ad hoc techniques in a cipher is we like to rewrite the cipher specification a little bit into an equivalent representation. Very famous example being we have a normal specification of the round function like skinny here. And sometimes it would be more convenient to have this key addition in a different place on the other side of the linear layer for an equivalent subkey technique, for example. Now, sometimes this is relatively obvious when it should happen and when it should not happen. But ideally, this is also something which the tool could try to optimize for us. Like if it could choose on the fly for this particular attack description or so, does it make more sense to do it here or to do it in some other ways or to introduce other kinds of rewrites? Another example that we had in one of our own papers is the case of key recovery with the help of the fast Fourier transform, where we need the function that we model to be of a specific structure. Namely, it should be a fixed function of an XOR of the ciphertext and key. And the specific example we had was, I think I have a picture from some of the graph that we generated. So the thing is that this function was a Feistel function. And in Feistel, you're a bit flexible in moving around the keys that you have between the rounds. And this means that if you just set up the function description directly, it looks like you can't get very far with FFT. But if you restructure this dependency graph a bit and try to get it into exactly this shape here, you can do a lot more. And being able to do something like this on the fly would be super convenient as a cryptanalyst. Okay, so that's, I think, what I wanted to say on the cipher description level. Now let's talk a bit about the precision of the results that we are getting. So on efficiency versus quality trade-off. Here we've also seen already quite a few examples today. So in particular, several people talked about distinguishers that are based on combining multiple different trails. We saw examples of differential linear distinguishers or very similarly boomerang distinguishers, but you could also phrase the miss-in-the-middle approach to impossible differential attacks as an example of this. And what exactly is the challenge here? We do know how to model the individual parts of these distinguishers, but it's not quite trivial to decide how to connect the two. One example where it's not trivial is what Patrick talked about in the impossible differential case, where you sort of have, so when he talked about the previous work, where you sort of have to make a decision of where the link between the two trails is. And this is necessary in order to be able to detect certain contradictions, in particular indirect contradictions. Or, of course, the fact that when we do model differential linear or boomerang attacks, it usually doesn't look like this. It looks more like this. So we are not connecting the two distinguishers directly, but there is some sort of sandwich layer in the middle, which needs to take properties from both sides into account. And being able to decide how long these parts should be, where they should be, and so on, is also something where tools can definitely help, but where we need to be very careful in how we encode this. We can combine trails, of course, not only sequentially, but also in parallel. And actually, we are very often interested not just in one particular path between two endpoints, but what we're actually interested in is a whole collection of trails with respect to some particular constraints. So often we actually run into a sort of, I would call it a two-level optimization problem. So as an example, what we currently often do is we first find one good differential characteristic, and then we try to figure out, is there a strong differential clustering effect? Are there many trails contributing to the same differential? And we can ask the same question in the linear cryptanalysis context with respect to linear hulls, might be even more relevant there. We can also ask about this with refined models such as quasi-differentials, for example. So in all of these cases, we usually first look for one thing and then try to extend it and are actually interested in the quality of the overall thing, so of the second optimization layer, instead of the first one that we are working first. But this is very hard to handle. There are different ways of tackling this. Currently, we mostly use this greedy approach of first judging one thing and then extending it. But there are a few alternative things we could do, and a few related areas where this pops up, which are not just about trail clustering. So in particular, in several attacks, we have the situation that we not only want to list individual trails, but we want to find a sort of collective description of a set of trails. Or we want to represent the fact that we only have partial knowledge about a family of trails that we are studying. So an example is if we study, let's take the example of differential cryptanalysis again. Very often for an attack, it makes sense not only to look at the clustering effect and keep the input and output difference fixed, but we can study, for example, truncated or partially truncated propagation. And actually what we could let a solver do is not only allow the usual probabilistic transition between, so from one differential mask to the next, but at each S-box, for example, we could give the solver a choice. Do you want to choose only one specific output difference, which introduces some probability? Or do you prefer at this point to just deduce everything you can about the output and do a deterministic propagation? And at each S-box you could choose, and at the end you're trying to optimize the distinguisher that you still have as much distinguishability as possible, while at the same time minimizing the probability that you're working with. And in particular, this makes sense when shifting from the distinguisher view to the full attack view, which includes some key recovery steps. Because in the key recovery steps, most of the time we do pure deterministic propagation, though we've heard an example today where we also heard about probabilistic propagation, which would be also an instance or an example of this. And so this is from an old paper where we tried to describe the whole attack based on this kind of differential view. And at each step, we had multiple allowed differences. So we tried to characterize the set of relevant differences in a particular round. This leads to a sort of attack view where the boundary between the distinguisher and the key recovery phases is a bit blurred or isn't so clear anymore. It's misaligned in the terminology that we heard earlier today. All right, and finally, one other example where we're looking at families of cases is in a guess and determine attack context. I think I'll not go into the details of this, but instead jump to the next direction, because it's kind of the opposite of what I just said now. So on the previous slide, we had too many trails, but we can also be interested in the case where there are no trails at all. And a few examples we've already heard. So this includes impossible differentials or zero correlation approximations, or in integral cryptanalysis, the case of division and monomial trails. And this comes with its own specific challenges. I'm also not going to talk about this in too much detail because there have been several very interesting talks about this today already. I just want to mention or re-emphasize the point that we've already heard, that we can model this kind of thing with positive or negative models. And if we want to connect it with other things, we need a positive model, or we need to switch to a more powerful type of modeling language. So something that we are not yet really using in cryptanalysis, but that could potentially be helpful, is something like quantified SAT solving. So where you can use existential or for all quantifiers when expressing what you're looking for. Unfortunately, these solvers tend to be super slow. So I'm not sure they are the right solution, but it's maybe something to try out. One very special challenge in this context that we're certainly not going to be able to solve just with tools, but with some more theory, is proving the absence of such absence-based distinguishers. So in purely positive models where we just search for trails, we can make such absolute statements like there is no trail with fewer than this and this many boxes. But it doesn't really seem to be feasible in a tool-based approach to prove that there is no impossible distinguisher. Even though on paper we often can easily gain confidence after which number of rounds there is no more distinguisher, but on a tool-based view we can also always only prove this in a very restricted sense, because if we try to do it with positive models, we might just run into the problem that our description language is a bit too abstract. Whereas if we try to do it with a negative model, we have the issue that we would have to enumerate all possible distinguishers to test them. So this is also not feasible. Okay, so this is for the degree of detail, so to say, that we can look at for distinguishers. Finally, I do want to say a few things about optimizing full attacks, because this is what I'm really most interested in all of this. And this is because the overall challenge is to even describe what we are looking for. Because for this, we need a solid theoretical model of what we are searching for, or of the attack architecture that we're aiming for. And there are areas of cryptanalysis where we do have some reasonable approaches for this, but there are certainly areas where this is less the case. I would say one of the more solidly analyzable area is the case of block ciphers based on some standard distinguishers like differential, linear, or integral ones. So there we have a relatively clear architecture typically. We have a distinguisher part, and we can extend it by a few rounds, and we can try to separately deduce some bounds on each of these parts to get an overall view. And if we are looking for specific cases, so if we are taking the cryptanalyst hat, we do have good methods of searching for individual distinguishers. And we have some first attempts at the key recovery part. One of the challenges with the key recovery part is that it's not entirely clear what type of result this should be returning, because what we're actually looking for is an attack description. So we would need to write models that return algorithms. Now, of course, they can't write them from scratch, so we need to somehow parameterize what we are looking for, or try to find which decision variables would really make sense here. We have a much less clear picture, I would say, if we go towards unkeyed functions like hash function cryptanalysis or permutation-based cryptanalysis, because there is not really this clear distinction into, or the best attacks are often not really based on such a clear separation into different phases that we can separately study. There are a few cases where it works okay, like for example, if I'm looking at some sponge constructions and at the permutations in there, if I have a particular target in mind, I can, for example, say which type of differential distinguisher could be useful here. But unfortunately, these purely distinguisher-based attacks are usually not the best ones in hash function analysis. What we're instead very often doing is something that looks more like this. So this is also from an old paper, also targeted an unkeyed setting. And what we see here is sort of the logical flow of the attack. So it starts easy. So we start simply going from the bottom down, but at some point we are taking very roundabout ways to deduce what we are looking for. So we start guessing things somewhere here, and then we go through different paths in the cipher and take a lot of detours, and at the end we try to verify a property somewhere in the state. So there is no longer this clear linear structure that we are following that we usually have in either the distinguishers or many key recovery attacks. And so if we try to model something like this, it's really hard to define what is the architecture of this type of attack. How do we generalize this type of algorithm? We need to model somehow that we have different steps. We need to model somehow that we can choose things and deduce things, but overall it's relatively messy. There have still, okay, it gets even worse if we look at arithmetization-oriented primitives. This was the main point of Leo's talk, I would say. Okay, there have been a few attempts at doing this and at defining these ingredients. So these ingredients here, defining which search space we have, which are the variables we can choose, and what we can deduce or learn from this in order to evaluate the quality of our current solution. So this includes the autoguess tool that was mentioned earlier already in Hossein's talk, which is a sort of guess and determine approach where we try to guess some key cells and deduce some other target variables in a multi-step approach. And this can be seen as a basis for several follow-up works, either in the case of key recovery for differential attacks or key recovery for integral cryptanalysis like this graph restructuring example we've seen before. Okay, so this is the eventual goal that we have, optimizing full attacks. And ideally not by analyzing the distinguisher and the key recovery separately, because the best possible distinguisher doesn't necessarily make the best possible attack. But ideally in a joint way. But even if we do it separately, it's hard enough on its own, because there are so many different ad hoc optimizations that we can do in this area. All right, so what could a final output of a solver that does search full attacks look like? Ideally, it should be in this algorithm format. So for example, something like this. So the tool should find some sort of distinguisher, and then additionally, a sequence of steps how to execute a certain key recovery strategy, what the cost of each of these steps is, how this influences the overall cost, and so on. Okay. So this is challenging, first because it's not always easy to create such a joint model, easy or efficient. It puts some constraints on the types of distinguishers we're looking for, but it also forces us to have a clear mental model of the flow of our attack and the choices we can make. Even when we have described these choices, it is not always easy to get an accurate formula for the complexity of the resulting attack. This has a number of reasons. Often we only have bounds, which make some simplified assumptions that are not necessarily true. Often the complexity formulas have multiple parts. It's not as simple as, for example, the probability or correlation of a trail, where we can just sum the cost of the individual or the weights of the individual parts. It's often more complex. We heard earlier, sometimes it needs helper variable, which are a bit unintuitive and so on. And it needs a clear and deep understanding of how the attack works. Very often it's multi-step processes. The more steps we aim for, the heavier the models get, so the harder they are to solve. One thing that I haven't yet mentioned at all, but that is, I think, also very relevant, is that, of course, if you look at full attacks and key recovery attacks, you need to take the key schedule into account. And in the world of key schedules, we have a lot more variability than in the world of state update functions. And they have completely different impacts on different types of attacks. So something that may be easy with a trivial or linear key schedule can be completely infeasible with some type of strong nonlinear key schedule, for example. Okay, and finally, there are tons of different optimizations, some general techniques, some ad hoc tricks, which are not really categorized or mapped and often incompatible with each other. And you really have to make a selection beforehand of what you want to take into account and what you kind of skip. Okay, so to conclude, these are, I think, the main levels where we are still facing challenges or trade-offs that we need to make. And of course, for an ideal framework, ideally, you would like to be able to choose any possible combination of all of these trade-off ranges and get a result. I think that's a bit too optimistic, but at least it's something to aim for. All right, so thanks a lot, and maybe you have some questions.
Any question? Everybody's super tired. Okay, then maybe we can go to the next talk. Let's thank Maria again.